So this is the concepts video for Kinetics 1, determination of the rate law of an iodine clock reaction. And an iodine clock reaction is a neat thing. We're going to talk about that in a minute. But first, we're going to talk about what we're going to be determining the rate law for. Where you have two iodides and a persulfate ion reacting to form iodine and two sulfates. So what we're going to be doing first of all is we need to remember have those change in concentration and rate chart where we change the concentrations and see what happens to the rate. Okay, and if you don't remember this, take a look at your pre-lab quiz, and that's what we're talking about. So we're going to be changing the concentrations of these and studying what happens to the rate as we do. Now, how do we determine the rate, though? It's easy to change the concentrations, but how are we going to figure out that initial rate? And the way we do that is by our rate of appearance. So we've got two things. We are doing our section 2 from our kinetics, where we determine the rate law, and section 1, where we're talking about, in this case, the rate of appearance. Now, you can tell that iodine's being formed because it forms sort of a brownish solution. So you can actually see iodine being formed. But if we were to change the concentrations of iodide and then hold the concentrations of iodide steady and change the concentrations of persulfate, even though this is a relatively slow reaction, we really wouldn't be able to distinguish any difference in the rate for the multiple reactions. Okay, so since these happen such that our rate wouldn't be particularly distinguishable, we're going to have to figure out, and we're going to have to make the experiment such that we can measure this rate. Because once we have done this, once we know those rates, we can do the comparison like we did in class to find the rate law. Now we know rate is equal to K, which is our rate constant, times the iodide to the M and persulfate to the N. And it's the M and the N that we're going to be figuring out. So this is fairly straightforward. We've done this a million times, and the rate of appearance seems to be a fairly easy thing to do. So what we need to do is extend that time that it takes for the iodine to appear. So here, if we had our starting time and we had a certain concentration of iodide and a certain concentration of persulfate, let's say we have 3 of them. As it stands now, this one has this amount of time, this one has this amount of time, and this one takes this amount of time. And trying to tell the difference between these to get our change in iodine concentration per change in time would be almost impossible. So we've got to stall it. It's kind of like the analogy of watching runners on the track. If you have a very fast runner at the starting line and you have a very slow runner at the starting line, if you listen for the gun and you both take one step and then try to measure it, the difference between the times, you're not going to be able to. So what we need to do is, like with any race, they have to run a certain amount of time and then, or a certain amount of distance, and then you can distinguish between the rate at which they're running. That's what we're going to do. We're going to give this reaction a period of time in which, and it's going to be the exact same period of time, in which to react so that we can distinguish between the 3 different concentrations. Okay, so this is how it's done. This is the clock reaction. Here we have the iodine that has been made up here in the original reaction. Okay, the one that I circled up here. Here's the iodine that has been made. But instead of turning brown before it has any chance to do anything, it is gobbled back up by something called thiosulfate. It's a thiosulfate polyatomic ion. And that thiosulfate turns it back into iodide. Okay? So down here, if we look at this, this is the overall reaction. Here we have the reaction that we're interested in, the persulfate and the iodide reacting to give sulfate and iodine. But we're going to put in this thiosulfate so that we send that iodine back to being iodide over and over and over and over, and then all of a sudden there's no more thiosulfate and the iodine can be detected. Now we want to make that iodine detected a little bit better than this faint brownish color change, so we are adding starch. And as some of you may have seen in high school biology, starch and iodine form a dark blue. Okay, form a dark blue. So what we're going to do is do this with all of our different concentrations, and depending on how fast this goes, your iodine, how fast this iodine is being produced, it still has to react with the same concentration of thiosulfate. Same concentration of thiosulfate. So again, if we're a fast reaction, we're going to use up that thiosulfate fast. If we're a slow reaction, this is slowly being produced, you're going to use up the thiosulfate slowly. Okay? So all this starch is the indicator. Tells us when we have iodine that's actually staying in solution, that's not being used up by thiosulfate. So slow reaction, this thiosulfate gets used up slowly, and it takes longer before you get that blue complex. Fast reaction, the iodide gets used, the thiosulfate gets used up quickly, and it's less time before you see that blue complex. So that's the idea behind this lab. Hopefully you will remember how to actually figure out your rate law. Remember again, you're going to be having iodide, the concentration of iodide, and the concentration of persulfate, and a rate, which you're going to find from delta I2 over the change in time. Okay? And you're going to have 3 different reactions. You're going to measure the rate by the time. I'll show you in a second how we get the change in iodine. And you are going to be the one who makes these different concentrations, so you'll know what they are. Okay?